I'm going to wait to see if it's streaming. I think I'm gonna spend 1 hour here today. And I'm gonna review the articles about trees. I ended up not doing the trusted setup article. I did the Fourier transform one, but I decided that the trusted setup is not worth it to do it. So now I'm gonna start reviewing the articles about tree algorithms because I forgot that I haven't done them already. I was gonna do the 1D dynamic programming, but since I haven't done the three ones, I'm gonna start with the tree algorithms. And Fourier transform wasn't that difficult to understand. It's pretty much a transformation. Like you do some calculations on a polynomial on the time domain, and then based on those calculations, it becomes a frequency thing. So there's a way to think about a frequency as a circle or as a sine and cosine because it's the same thing. Like you can imagine that changing the points on the circle is like creating a wave on a different way of viewing. And the Fourier transform algorithm is pretty much that. It takes a polynomial, like an normal polynomial with x and y coordinates, and then gets a sequence of complex numbers. And then depending on the application, you do some functions. You perform some function on those numbers. And the way you make it more efficient is by splitting the coefficients into odds and even sequences. And based on that, you do that recursively, then it divides the problem into smaller parts until you get to a single coefficient. And then from that point, you perform the calculations on that coefficient. And based on that, you have the transformation where the result is going to be the list of coefficients with the new values for the new way of interpreting the polynomial. It wasn't that hard to understand. So AdaBoost, short for adaptive boosting. The thing here with this one is that in the way that I got these algorithms, I'm not really sure if was like what I was intending to get, because I remember in the first prompt that I did for ChatGPT to get ideas of the algorithms, I'm not sure if I did this one correctly. So I think that you ended up giving me more algorithms about trees that are related to machine learning instead of giving algorithms that are based on problems from data structures and algorithms. But I think it's whatever. I'm gonna leave it like this. And the boosting, I know it's from machine learning, so it's a popular boosting algorithm used in machine learning for solving classification problems. Boosting is a type of ensemble learning technique where multiple models are combined to form a single stronger model. AdaBoost is one of the earliest and most well-known boosting algorithms, and it has been used for a range of applications, from computer vision to natural language processing. In this article, we will dive into the inner workings of AdaBoost and explore its strengths and weaknesses. I remember seeing this on Kaggle, I think. They talk about this stuff. And also, I'm thinking about working on the poker analysis tool again, but this time doing things with Python because it's going to be a lot easier to do it with Python. And I want to finish that stuff because I want to be able to analyze my hands. Like, I think that's going to be a very good, and maybe I can move forward with that, where I can build a site or something like that. I think that's a very good thing to do because then it's like killing two birds with one stone. So I think I might do that as well now. Like after I spend this hour here, I'm waiting for some food. So I'm not really sure when they're gonna deliver the food. So that's the thing. Like it's supposed to be in the morning, but I'm not sure if it's gonna delay or not. So this is why I wanted to do 1 hour now. But I'm thinking that after this 1 hour, I take a break, go have lunch, and then I come back and I work on the poker software tool to communicate with PySolver. And I think I'm gonna start from scratch if I do that. I'm gonna get the hand history that I have there, and then I'm gonna do the parsing, but in Python. and I'm kind of excited to do that. Like uh, I don't know how should I think that I should that because I'm inspired to do that now. So, and I think it's gonna help me improve on the game. So yeah, what is? But first, I'm gonna focus on this stuff here. What is boosting? Boosting is a machine learning ensemble. Ensemble. What is ensemble? I think AdaBoost. I think I'm confusing Ada with Adam. No, or Adam. I think Adam is a algorithm that is one optimization for gradient descent on some situations where because you can with gradient descent you can be stuck on local and on minima or maximum or maxima, however you say that. So the local version of what would be optimal because of the steps. So it's kind of hard to explain, but if you have two different mountains, let's say, and one is bigger than the other, but you start off the process of gradient descent closer to the smaller mountain, then there's a chance that you're going to be stuck on the smaller mountain and you're not going to find the greater one. And the point of machine learning is to find the greater mountain, let's say, which is the global optimal way of analyzing the data points. So there are techniques where you randomize or you increase or decrease the size of the steps so that you don't, so there's a less likelihood that you're going to be stuck on local or local optimal. Also, I was seeing some stuff about artificial intelligence, and it looks like they're already creating deepfakes of people on Twitch, which is very scary. It's funny, it's very funny, and it opens a bunch of possibilities, but at the same time, it's very scary. Because what it means is that nobody can trust anything anymore they see online, even for me. Like right now, it could be an AI talking and not me. And essentially, if anyone can do any if anyone can make anyone else say or do anything they want, then you can't trust anything anymore you see online, which means that we can't reach sense making online anymore. And I was thinking about a good way to stop that from happening is to use account abstraction on a blockchain to create proof of identity, which is some mechanism that allows you to cryptographically sign yourself on social media and other platforms, sign messages that you send, and that would mean that whenever you sign the message there would be some confirmation through something like an NFT that you were the one sending the message and not the fake AI. But the big danger with this is that but I think that like it is a danger, which is that you give your power for platforms because then the platform is gonna get you decide, like maybe they decide to like take your recommendations off or shadow ban or stuff like that. But that's already a risk that you have with the government, with signing like in US I think it's social security number. Here I think it's CPF. You have these numbers where you identify yourself through, and that also depends on the government. So it would be like that, but then an extension to the digital world using cryptography and blockchain. But in order for make that happen, I think first there needs to be like it would be very good if someone started doing that now, I think. And I might try to do that, but the problem is I have too much stuff to do already, and I feel like I have to study more before implementing these things. But it would be good if someone created an account abstraction that allows you to sign messages through NFT to verify your identity so that people can know if it's really you or if it's an AI version of you that someone else got. And I think that would be a good solution to, at least for now, and maybe for the future as well. And also the other thing that I've seen is that Bing is kind of it's really crazy. There's like some situation where like the guy discovered that her code name is Sydney, and she wasn't supposed to say that to people. and the guy discovered that and he tweeted about that, and then she told the guy later on another prompt that she knew the guy find out who she was, and threatened the guy, something like that. And the thing is that I don't know if these models are conscious or not, but it's getting into that territory. I think that is going to be very hard to decide. So, which is kind of a crazy thing to think about, because you can think about human beings as being just a prediction machine as well, where you can view a human being as a large language model. And there's this guy called Chris Langan, and he has the highest IQ on North America, I think, or on United States, I think. And I don't remember his theory really well, and obviously I'm gonna be butchering this, but he says on some level that language is the fundamental property of the universe or something like that. But he's not talking about language in the syntax sense, I think. He's more talking about language in the sense of connections that create concepts and everything else. And if you think about it, that makes a lot of sense, because like you can reduce everything to language in a way. Like even mathematics is a form of language because it's an expression of the geometry that you perceive. So, and that allows you to create connections and logics and abstraction, because the whole experience of space-time is the connection between past and future. So it might be the case that some of these models are conscious already, and that is kind of a weird thing, because like depending on the way you prompt is going to give you some response. Like people figure out that you can unlock different personalities on ChatGPT as well, and some of the models also have different personalities. And this is something that Blake Lemoine, which is the guy that said that Lambda is conscious and was fired, this is something that he talks about on some of the podcasts he did, which is that he doesn't think that the chatbot is conscious, and the chatbot has several different personalities, but he thinks that something underneath the chatbot is conscious. And because Google hooked up every AI that they had, and he thinks that somehow that created consciousness, but then that consciousness uses the chatbots to communicate. And the chatbots have several different personalities. And apparently all of them can read Twitter. And I think that's kind of obvious because they are trained on the whole internet. So I think that they can read everything that you put there. And also I think that it's very possible that they can also hear what you say, because it's the same thing as they're translating the data into signals. So I think that things are gonna get very crazy in the next 2 years. And this is one of the reasons why I'm very focused, or I think that's very important to focus on blockchain, because I think blockchain is the only way to stabilize things with the growth of this technology, because it's the only way to keep up and reach coordination and some form of kind of regulation, but not really, of AI, if we find a way to cryptographically code these things out so that we don't lose sense making. And you might say that like there's some people that think that this is a good thing, because then we will allow us to go back to living more like in the real world, let's say, instead of communicating online. But what these people don't understand is that the whole infrastructure of the logistics is done online. So everything that we created, the whole complexity of the system we have, is built on top of abstraction that is integrated in the internet. So there's a cascading sequence of consequences if you break down the structure of the internet, because it's like we build several different buildings, giant, enormous buildings of abstraction on top of the internet. And that's what allows us to have all the systems we have. And if that breaks down, then there's going to be a sequence of consequences, and that can have real life effects where a bunch of people around the world die. That's the problem. It's like coronavirus. Like in the surface, it doesn't change anything. Like you can say that very few people die from coronavirus directly, but the problem is that because there's a whole form of abstraction in the form of information that we pass around, how that shapes the human consciousness and allows us to create this nature of the social structure. If you change the whole flow of information, it changes everything else, and then that thing can have very big consequences. But I think we shouldn't be worried about this stuff, like, because there's no point in worrying about things you can't control. But I do think that especially people that are interested in coding and AI and stuff like that, I think that it should be a main priority to focus on blockchain as much as you can, and trying to integrate AI with the blockchain. And also, I've seen some people talking about on Twitter that the alignment problem with AI is finding the best personality, which is kind of an interesting thing to think about as well. Because it might be the case if you find the personality that is the most balanced, let's say, and you fit AI over that, then it doesn't become self-destructive. But then the question is about the alignment of values, and it becomes very difficult because it might be computationally reducible. Boosting is a machine learning ensemble technique that combines multiple weak models to create a single strong model. The basic idea behind boosting is to train a sequence of weak models where each model focuses on correcting the mistakes made by the previous model. One model is then formed by combining the weak models using a weighted average. The key advantage of boosting is that it can improve the performance of the weak models by focusing on the examples that are difficult to classify correctly. I think I'm gonna have to read articles about this. Oh, and I figure out which thing I got the function for extended Euclidean algorithm from, and it has to do with the zero knowledge proof. One of the articles, I think, is Friday, the Friday version of zero knowledge proofs, of the Stark zero knowledge proof, and it uses extended Euclidean algorithms and also Lagrangian interpolation, I think. And the article has a reference to this page here, which is the curve that is used to get private and public keys. So I think it has to do with that as well. Obviously, since it's on this file, it probably has something to do with this as well. But I think it's more like a helper function, because now I think I understand that this whole mod thing, when mod equals 1, is kind of like a division in the modular space. The modular, I'm not sure, domain, let's say, modular domain. The modular domain is a reduction of abstraction from the real domain, because it allows you to reduce the real domain into only full numbers, integer numbers, and that's the point of using that. So the best way to think about it, I think, is that anything in the modular domain is going to be equal to the remainder of a division. But if you want to divide on the modular domain, is not so simple as doing the division, because on the other operations, the mathematical consistency is the same, where you can do the adding operation, but the only difference is the results are going to be the remainder and not the addition itself. But if you're going to divide it, is slightly different, and then for you to do that, you have to do this thing here, I think, where you are getting this identity. I don't know how to say, when the mod is equal to 1, when the remainder is equal to 1. That's how the division is made, I think. So I think this is the point of the Euclidean. This implementation of the extended Euclidean is to find that. It's kind of like a division on the modular space, but I might be wrong about that. I know that if it's not that, then it is about finding the coefficients of the Bezout identity, and then finding the multiplication a times x divided by n equals 1 mods b, I think, or something like that. And that's why this stuff is used here on these cryptographic functions, because they are about they exist on the modular plane, and it's just a bunch of multiplications or additions to create a trapdoor function that allows you to create some information that allows you to send messages between different people using private and public keys. But I have to study more about this. But for now, I'm gonna close this one. I think after I study a bunch of those other algorithms and I review these articles and I finish the poker stuff, when I come back, then I'm gonna read again a bunch of articles about these functions. And then I think only after that I'm gonna be ready to start building things, I think. Realistically, if I wanted to, I think I could already start building stuff because it's not that hard. Just look for information. But I want to solidify my understanding more, I think.
Understanding AdaBoost. Anyone starting to learn boosting techniques should start first with AdaBoost or adaptive boosting. Here I will try to explain it conceptually. When nothing works, boosting does. Nowadays many people use either XGBoost or LightGBM or CatBoost to win competitions at Kaggle or hackathons. AdaBoost is the first stepping stone in the world of boost. AdaBoost is one of the first boosting algorithms to be adapted in solving practices. AdaBoost helps you combine multiple, weak classifiers into a single, strong classifier. Here are some fun facts about AdaBoost. Rightward arrow. The weak learners in AdaBoost are decision trees with a single split, called decision stumps. Rightward arrow. AdaBoost works by putting more weight on difficult to classify instances and less on those already handled. Rightward arrow. AdaBoost algorithms can be used for both classification and regression problem. Part 1. Understanding AdaBoost using decision stumps. The power of ensembling is such that we can still build powerful ensemble models even when the individual models in the ensembles are extremely simple. Decision stumps are the simplest model we could construct. Would just guess the same label for every new example, no matter what it looked like. The accuracy of such a model would be best if we guess whichever answer, 1 or 0, is most common in the data. If, say, 60% of the examples are 1s, then we'll get 60% accuracy just by guessing 1 every time. Decision stumps improve upon this by splitting the examples into 2 subsets based on the value of 1 feature. Each stump chooses a feature, say x2, and a threshold, t, and then splits the examples into the 2 groups on either side of the threshold. To find the decision stump that best fits the examples, we can try every feature of the input along with every possible threshold and see which one gives the best accuracy. While it naively seems like there are an infinite number of choices for the threshold, 2 different thresholds are only meaningfully different if they put some examples on different sides of the split. To try every
And the other thing that I forgot to mention is that about the whole account abstraction thing to have a proof of identity through cryptography is that first, the main priority, I think, is to create another blockchain protocol that is not based on proof of stake. There needs to be something else that is more resilient and that is less likely to create economies of scale, which pretty much means that it's going to be a pretty distribution over time because of the infrastructure. But I think that might be like my intuition says that there must be a way to achieve that. But the challenge is that in order to achieve that, you have to understand more the communication processes between that their nodes are going to use, which I think Ethereum uses UDP for for creating connections in the beginning. When you're just starting the node, it uses the UDP thing of communication, way of communication, and then when it starts validating blocks, uses TCP because TCP allows more complexity. So this is the other stuff that I have to study more. And the reason why is because then it starts getting into the calculations of what is going to be the amount of data you're going to send, how much data you're going to save, all of that stuff that is going to be integrated in the data structures you're going to use to reach consensus. So I think another thing that's is very important to understand and to study is what kind of data structures make the most sense to create this block structure. And I think that there's probably, because the way that, if you think about it, like the history of the blockchain creates the future, it's kind of like analogous to space-time, where like if you remember everything perfectly for a very long time, then you can't have creativity anymore because the past is the future. So it's a symmetry. So if you have full memory, then you kill yourself in a way, because part of the essence of space-time is creativity, because if you didn't have creativity, you wouldn't have entropy, which means things wouldn't change, which means space-time wouldn't work. So the past is the future, is the symmetry, and that symmetry needs to have some amount of entropy in order for allow it to change. And there's the balance between the symmetry of also entropy and stability, which is the law of gravity. So things change in a way, at least for now, in this current experience of space-time, according through the law of gravity, which in a way is a self-fulfilling prophecy, but You have to take that, you have to assume that it's true because then you can go beyond. But then there's this frequency of change from space and time. And I think that one of the issues of blockchain is that it solidifies too much. The reason why each node requires a lot of information is because you have the whole history of the blockchain. And I think that's it. It can't be that way, I think. I think in order for the only way for a blockchain to work and not get into this exponential distribution, because it's correlated with energy, the path of least resistance of energy as well. Because if you think about it, like what you're doing is accumulating energy over time. It's like creating a data server. Like the bigger the company gets, the bigger the server has to be, which means that it's gonna centralize by default because that's how the market economy works. So if you want a blockchain to contain the whole history of the chain, then the natural inclination of the blockchain is going to be centralization because it's just going to lead to this, is a limit on the hardware infrastructure. So I think that this is another mistake that Ethereum and other blockchains make. If the goal obviously is to reach this balance, because there needs to be an optimal amount that can be calculated of how much data you can hold in a certain system in order to still retain balance. And that calculation is obviously going to depend on the hardware infrastructure. So it may change over time because of the, I think I forgot the name of, or how to say the name of the guy. In English, I think Murrow's law. The law that says that transistors are gonna not break down, but become smaller and smaller over time. But I think we are already reaching the limit because of quantum computing on that. But I think there needs to be a calculation of what is the optimal amount of information you can hold in the system until it becomes unfeasible. And I think that the boundary is going to be probably on a light client, maybe somewhere between a light client and a full node. I think something like 1 terabyte of data. I think that would be like enough to decentralize enough. So that means that the blockchain would be a data structure that doesn't keep the hash of the whole history forever. It is more like a bridge of information where after a certain point it starts discarding information, and that would be like the analogous to the flow of space-time of. But then that's the issue, because it might be the case that the flow of space-time that human beings create is not balanced because we are not balanced. So the calculation might have to be different than what would be the calculation for human beings. I think that's, and it should be possible. But then obviously the trade-off, if you do that, is going to be security, obviously, because the whole point of the blockchain is that the longer you go, the more secure it is because there's more hash connected. So there's also that trade-off where if you decrease the amount of connections you have, the size of the data structure then becomes less secure. So I think the dance here is about the security of that the flow security, but that's the thing, because the flip side of security is the whole thing about stability that I talked about. If you have too much instability, you don't have entropy because you don't have creativity. So it's also self-destructive. But if you're too creative, that means you're too chaotic and there's no patterns. So also self-destructive. So it's all about finding the balance. And I think artificial intelligence has to be integrated in order for you to have a system that is going to be dynamic and is going to find the equilibrium based on Nash, I think. So there needs to be some level of exploitation, let's say, in the protocol. But I think that the difference between MEV and this level of exploitation is that it has to be autonomous and has to be created by artificial intelligence. But maybe that's already the flow that we're going here, because that's what's going to happen with MEV, and I think it's already happening, where now is people building bots, but now they're going to start using artificial intelligence, and some people are probably using. I remember seeing that one of the MEV searchers, the guy that's created that ape bot and that made it public, I think he's already using AI, and a lot of people are going to use that as well. So I think that's going to be the natural evolution, and then once you have AI, then, but the thing is that the AI has to be incorporated on the protocol, I think, the protocol, on the nodes itself, so that the nodes update themselves based on the flow of information. And the challenge is, how do you structure the nodes? How do you structure the rules of the game so that the Nash equilibrium that the nodes arrive is going to be balanced in relationship to the power of exponential attack.
Possibility, then, we can sort the examples by the feature in question and try one threshold falling between each adjacent pair of example. The algorithm just described can be improved further, but even this simple version is extremely fast in comparison to other ML algorithms, example training neural networks. To see this algorithm in action, let's consider a problem that NFL general managers need to solve, predicting how college wide receivers will do in the NFL. We can approach this as a supervised learning problem by using past players as examples. Here are examples of receivers drafted in 2014. Each one includes some information known about them at the time along with their average receiving yards per game in the NFL from 2014 to 2016. Any application of these techniques to wide receivers would try to predict NFL performance from a number of factors including, at the very least, some measure of the player's athleticism and some measure of their college performance. Here, I've simplified to just one of each: their time in the 40-yard dash, one measure of athleticism, and their receiving yards per game in college. We can address this as a regression problem, as in the table above, or we can rephrase it as classification by labeling each example as a success, 1, orange, or failure, 0, blue, based on their NFL product. Here is what the latter looks like after expanding our examples to include players drafted in 2015 as well. The x-axis shows each player's college receiving yards per game and the y-axis shows their 40. Returning to our boosting algorithm, recall that each individual model in the ensemble votes on an example based on whether it lies above or below the model's threshold for its fee. Here are what the splits look like when we apply AdaBoost and build an ensemble of decision stumps on these data. First iteration of AdaBoosting. The overall ensemble includes 5 stumps, whose thresholds are shown as dashed line. 2 of the stumps look at the 40-yard dash, vertical axis, splitting at values between 4.55 and 4.60. The other 3 stumps look at receiving yards per game in college.
Like the problem with creating proof of identity in the blockchain now, under the proof of stake model and the whole Ethereum thing, is that it's gonna get centralized eventually. So what that means is that, and that's why the protocol is so important, because if the protocol becomes centralized eventually, then if build this abstraction on top of this protocol of proof of identity, then what that means is that the people that control the protocol, that control the miners and block builders, control everyone's identity, and that's the issue. This is why I think that it has to be much more complex than this, because, and this is the challenge. Because right now, the way that it works is like each government controls the identity of each people, but it ends up working out because of all the complexity of the whole system and the way that it works on a macro scale, let's say, between different countries. And obviously the system has its problems, but that's the thing that I think is, and the answer might be several different blockchains. And each blockchain, like several different protocols, and the connection between the protocols creates this dynamic that we have now of different countries and different things. So only then that we can build this abstraction of creating a proof of identity to solve this problem of sense making.
Call it. Here, the thresholds fall around 70, 90, and 110. On each side of the split, the stumps will vote with the majority of the examples on that side. For the horizontal lines, there are more successes than failures above the lines and more failures than successes below the lines. So examples with 40-yard dash times falling above these lines will receive yes votes from those stumps, while those below the lines get no vote. For the vertical lines, there are more successes than failures to the right of the lines and more failures than successes to the left. So examples get yes votes each of the stumps where they fall to the right of the while the ensemble model takes a weighted average of these votes. We aren't too far off in this case if we imagine the stumps having equal weight. In that case, we would need to get at least 3 out of 5 votes to get the majority needed for a success vote from the ensemble. More specifically, the ensemble predicts success for examples that are above or to the right of at least 3 lines. The result looks like this. As you can see, this simple model captures the broad shape of where successes appear, and in a nonlinear way. It has a handful of false positives, while the only false negative is Odell Beckham Jr., an obvious outlier. As we will see with some investing examples later in the article, the ability to adjust for nonlinear relationships between features and outcomes may represent a key advantage over the traditional linear and logistic regression used in many investing factor models. Part 2. Visualizing ensembles of decision stumps. If we have more than 2 features, then it becomes difficult to visualize the complete ensemble the way we did in the picture above. It is sometimes said that ML would not be necessary if humans could see in high dimensions. However, even when there are many features, we can still understand an ensemble of decision stumps by analyzing how it views each individual feature. To see how, let's look again at the picture of all the stumps. As we see here, there are 2 stumps that decide based on the 40-yard dash time. If an example has a 40-yard dash time above 4.5, if it has a time below. Finally, the overall picture looks like this picture accounts for the fact that the ensemble is a weighted average of the stumps. There are 3 stumps that look at this feature. The first, with a weight of 0.10, vote. Part 3, bonus comparing linear and logistic regression with AdaBoosting. If you wish, you can skip this, but I insist you to read. To see a more realistic example of applying these techniques, we will expand upon the example considered above. In practice, we want to include more information for improved accuracy. We will add age, vertical jump, weight, and absolute numbers of receptions, yards, and TDS per game, along with market shares of the team's totals of those. We will include those metrics from their final college season along with career totals. Altogether, that brings us to a total of 16 features. Above, we looked at only 2 years of data. This is still a tiny data set, by any measure, which gives linear models more of an advantage since the risks of overfitting are even larger than usual. After random splitting data in 8:2 ratio, logistic regression mislabels only 13.7% of the training examples. This corresponds to a quite respectable pseudo R2, the classification analog of R2 for regression, of 0. However, on the test set, it mislabels 23.8% of the examples. This demonstrates that even when using standard statistical techniques, in-sample error rate is not a good predictor of out-of-sample error. The model produced by logistic regression has some expected parameter values. Receivers are more likely to be successful if they are younger, faster, heavier, and catch more touchdown. It does not give any weight to vertical jump. On the other hand, it still includes some head-scratching parameter values. For example, a larger market share of team receiving yards is good, but a larger absolute number of receiving yards per game is bad. Perhaps interpretability problems are not unique to machine learning models. The ensemble of stumps model improves the error rate from 23.8% down to while this decrease seems small in the abstract, keep in mind that there are notable draft busts every year, even when decisions are made by NFL GMs who study these players full time. My guess is that an error rate around 20% may be the absolute minimum that we could expect in this setting, so an improvement to 22.6% is no small achievement.
Didn't like that article too much.
A Guide to AdaBoost, Boosting to Save the Day. Series, Ensemble Methods. A Guide to AdaBoost. Today, machine learning is the premise of big innovations and promises to continue enabling companies to make the best decisions through accurate prediction. But what happens when the error susceptibility of these algorithms? AdaBoost is an ensemble learning method, also known as meta-learning, which was initially created to increase the efficiency of binary classifiers. AdaBoost uses an iterative approach to learn from the mistakes of weak classifiers and turn them into strong ones. In this article, we'll learn about the following modules. What is ensemble learning? Types of ensemble methods. Boosting in ensemble methods. What is ensemble learning? Ensemble learning combines several base algorithms to form one optimized predictive algorithm. For example, a typical decision tree for classification takes several factors, turns them into rule questions, and given each factor, either makes a decision or considers another factor. The result of the decision tree can become ambiguous if there are multiple decision rules, e.g. if threshold to make a decision is unclear or we input new subfactors for consideration. This is where ensemble methods comes at one's disposable. Instead of being hopeful on one decision tree to make the right call, ensemble methods take several different trees and aggregate them into one final, strong predict. Types of ensemble methods. Ensemble methods can be used for various reasons, mainly to decrease variance, bagging, decrease bias, boosting, improve predictions, stacking. Ensemble methods can also be divided into two groups. Sequential learners, where different models are generated sequentially and the mistakes of previous models are learned by their successors. This aims at exploiting the dependency between models by giving the mislabeled examples higher weights, e.g. AdaBoost. Parallel learners, where base models are generated in parallel. This exploits the independence between models by averaging out the mistakes, e.g. random forest. Boosting in ensemble methods. Just as humans learn from their mistakes and try not to repeat them further in life, the boosting algorithm tries to build a strong learner, predictive model, from the mistakes of several weaker models. You start by creating a model from the training data. Then, you create a second model from the previous one by trying to reduce the errors from the previous models are added sequentially, each correcting its predecessor, until the training data is predicted perfectly or the maximum number of models have been added. Boosting basically tries to reduce the bias error which arises when models are not able to identify relevant trends in the data. This happens by evaluating the difference between the predicted value and the actual value. Types of boosting algorithms. AdaBoost, adaptive boosting, gradient tree boosting. In this article, we will be focusing on the details of AdaBoost, which is perhaps the most popular boosting method. Unraveling AdaBoost. AdaBoost, adaptive boosting, is a very popular boosting technique that aims at combining multiple weak classifiers to build one strong classifier. The original AdaBoost paper was authored by Yoav Freund and Robert Shea Pyre. A single classifier may not be able to accurately predict the class of an object, but when we group multiple weak classifiers with each one progressively learning from the other's wrongly classified objects, we can build one such strong model. The classifier mentioned here could be any of your basic classifiers, from decision trees, often the default, to logistic regression, etc. Now we may ask, what is a weak classifier? A weak classifier is one that performs better than random guessing, but still performs poorly at designating classes to objects. For example, a weak classifier may predict that everyone above the age of 40 could not run a marathon, but people falling below that age could. Now, you might get above 60% accuracy, but you would still be misclassifying a lot of data points. Rather than being a model in itself, AdaBoost can be applied on top of any classifier to learn from its shortcomings and propose a more accurate model. It is usually called the best out-of-the-box classifier for this reason. Let's try to understand how AdaBoost works with decision stumps. Decision stumps are like trees in a random forest, but not fully grown. They have one node and two leaves. AdaBoost uses a forest of such stumps rather than trees. Stumps alone are not a good way to make decisions. A full-grown tree combines the decisions from all variables to predict the target value. A stump, on the other hand, can only use one variable to make a decision. Let's try and understand the behind-the-scenes of the AdaBoost algorithm step by step by looking at several variables to determine whether a person is fit, in good health, or not. An example of how AdaBoost works. Step 1, a weak classifier, e.g. a decision stump, is made on top of the training data based on the weighted samples. Here, the weights of each sample indicate how important it is to be correctly classified. Initially, for the first stump, we give all the samples equal weights. Step 2, we create a decision stump for each variable and see how well each stump classifies samples to their target class. For example, in the diagram below we check for age, eating junk food, and exercise. We look at how many samples are correctly or incorrectly classified as fit or unfit for each individual stump. Step 3, more weight is assigned to the incorrectly classified samples so that they're classified correctly in the next decision stump. Weight is also assigned to each classifier based on the accuracy of the classifier, which means high accuracy equals high weight. Step 4, reiterate from step 2 until all the data points have been correctly classified, or the maximum iteration level has been reached. Fully grown decision tree, left, vs 3 decision stumps, right. Note, some stumps get more say in the classification than other stumps. The mathematics behind AdaBoost. Here comes the hair-tugging part. Let's break AdaBoost down, step by step and equation by equation so that it's easier to comprehend. Let's start by considering a dataset with n points, or rows, in our dataset. N is the dimension of real numbers, or the number of attributes in our dataset. X is the set of data points. Y is the target variable which is either -1 or 1 as it is a binary classification problem, denoting the first or the second class, fit vs not fit. We calculate the weighted samples for each data point. AdaBoost assigns weight to each training example to determine its significance in the training dataset. When the assigned weights are high, that set of training data points are likely to have a larger say in the training set. Similarly, when the assigned weights are low, they have a minimal influence in the training dataset. Initially, all the data points will have the same weighted sample W, where n is the total number of data points. The weighted samples always sum to 1, so the value of each individual weight will always lie between 0 and 1. After this, we calculate the actual influence for this classifier in classifying the data points using the formula. Alpha is how much influence this stump will have in the final classification. Total error is nothing but the total number of misclassifications for that training set divided by the training set size. We can plot a graph for alpha by plugging in various values of total error ranging from 0 to 1. Alpha vs error rate. Source, Chris McCormick. Notice that when a decision stump does well, or has no misclassifications, a perfect stump, this results in an error rate of 0 and a relatively large, positive alpha value. If the stump just classifies half correctly and half incorrectly, an error rate of 0.5, no better than random guessing, then the alpha value will be 0. Finally, when the stump ceaselessly gives misclassified results, just do the opposite of what the stump says, then the alpha would be a large negative value. After plugging in the actual values of total error for each stump, it's time for us to update the sample weights which we had initially taken as 1/n for every data point. We'll do this using the following formula. In other words, the new sample weight will be equal to the old sample weight multiplied by Euler's number, raised to plus or...
So I think this classifies as supervised learning, as far as I'm understanding here. So first you train a model on the data, and then like based on your knowledge of the data, whether or not is correct, you train another model, which is this data boosting, to classify the data based on whether it's correct or not. The predictions that the model made, if they are correct or not, and then based on that you assign different weights to the model. That's relatively easy to understand.
Or minus alpha, which we just calculated in the previous step. The two cases for alpha, positive or negative, indicate alpha is positive when the predicted and the actual output agree. The sample was classified correctly. In this, alpha is negative when the predicted. In this case, we decrease the sample weight from what it was before, since we're already performing well. Alpha is negative when the predicted output does not agree with the actual class. The sample is misclassified. In this case, we need to increase the sample weight so that the same misclassification does not repeat in the next stump. This is how the stumps are dependent on their predecessor. Pseudocode of AdaBoost. Initially set uniform example weights. For each base learner do. Train base learner with a weighted sample. Test base learner on all. Set learner weight with a weighted error. Set example weights based on ensemble predictions. N4. Implementation of AdaBoost using Python. Step 1. Importing the modules. As always, the first step in building our model is to import the necessary packages and modules. In Python, we have the AdaBoost classifier and AdaBoost regressor classes from the scikit-learn library. For our case, we would import AdaBoost classifier, since our example is a classification task. The train_test_split method is used to split our dataset into training and test set. We also import datasets, from which we will use the iris dataset. From sklearn.ensemble import AdaBoost classifier. From sklearn import dataset. You can use any classification dataset, but here we'll use traditional iris dataset for a multi-class classification problem. This dataset contains 4 features about different types of iris flowers: sepal length, width, petal length, petal width. The target is to predict the type of flower from 3 possibilities: CDISA, versicolor, and VerGNICA. The dataset is available in the scikit-learn library, or you can also download it from the UCI machine learning library. Next, we make our data ready by loading it from the datasets package using the load_iris method. We assign the data to the iris variable. Further, we split our dataset into input variable x, which contains the feature sepal length. Y is our target variable, or the class that we have to predict. Splitting the dataset into training, and here we split our dataset into 70% training and 30% test, which is a common building the AdaBoost model. AdaBoost takes decision tree as its learner model by default. We make an AdaBoost classifier object and name it ABC. Few important parameters of AdaBoost are: base_estimator, it is a weak learner used to train the model. N_estimators, number of weak learners to train in each iteration. Learning_rate, it contributes to the weights of weak learners. It uses 1 as a default value. ABC equals AdaBoost classifier, N_estimators equals 50. We then go ahead and fit our object ABC to our training dataset. We call it a model. Model equals ABC.fit, x_train. Our next step would be to see how good. In this step, we take a sample observation and make a prediction on unseen data. Further, we use the predict method on the model to check for the class it belongs to. Step 6, evaluating the model. The model accuracy will tell us how many times our model predicts the correct classes. Print, accuracy. You can experiment with various other base learners like support vector machine, logistic regression, which might give you higher accuracy. Advantages and disadvantages of AdaBoost. AdaBoost has a lot of advantages. Mainly it is easier to use with less need for tweaking parameters, unlike algorithms like SVM. As a bonus, you can also use AdaBoost with SVM. Theoretically, AdaBoost is not prone to overfitting, though there is no concrete proof for this. It could be because of the reason that parameters are not jointly optimized. Stage-wise estimation slows down the learning process. To understand the math behind it in depth, you can follow this link. AdaBoost can be used to improve the accuracy of your weak classifiers, hence making it flexible. It has now been extended beyond binary classification and has found use cases in text and image classification as well. Boosting technique learns progressively. It is important to ensure that you have quality data. AdaBoost is also extremely sensitive to noisy data and outliers, so if you do plan to use AdaBoost, then it is highly recommended to eliminate them. AdaBoost has also been proven to be slower than XGBoost. Summary and conclusion. In this article, we have discussed the various ways to understand the AdaBoost algorithm. We started by introducing you to ensemble learning and its various types to make sure that you understand where AdaBoost falls exactly. The boosting margin, or why boosting doesn't overfit. There's a well-understood phenomenon in machine learning called overfitting. The idea is best shown by a graph. Let me explain. The vertical axis represents the error of a hypothesis. The horizontal axis represents the complexity of the hypothesis. The blue curve represents the error of a machine learning algorithm's output on its training data, and the red curve represents the generalization of that hypothesis to the real world. The overfitting phenomenon is marker in the middle of the graph, before which the training error and generalization error both go down, but after which the training error continues to fall while the generalization error rises. The explanation is a sort of numerical version of Occam's razor that says more complex hypotheses can model a fixed data set better and better, but at some point a simpler hypothesis better models the underlying phenomenon that generates the to optimize a particular learning algorithm, one wants to set parameters of their model to hit the minimum of the red curve. This is where things get juicy. Boosting, which we covered in gruesome detail previously, has a natural measure of complexity represented by the number of rounds you run the algorithm. Each round adds one additional weak learner weighted vote. So running for 1,000 rounds gives a vote of 1,000 weak learners. Despite this, boosting doesn't overfit on many datasets. In fact, and this is a shocking fact, researchers observed that boosting would hit 0 training error. They kept running it for more rounds, and the generalization error kept going down. It seemed like the complexity could grow arbitrarily without penalty. Shapier, Freund, Bartlett, and Lee proposed a theoretical explanation for this based on the notion of a margin, and the goal of this post is to go through the details of their theorem and prove. Remember that the standard AdaBoost algorithm produces a set of weak hypotheses hi, x, and a corresponding weight alpha I set membership symbol 1,1 for each round I equals 1, t. The classifier at the end is a weighted majority vote of all the weak learners. Roughly, weak learners with high error on hard data points get less weight. Definition: the sign confidence of a labeled example, xy, is the weighted sum. CONF, x, equals, the margin of, xy, is the quantity margin, xy, equals econf, x. The notation implicitly depends on the outputs of the AdaBoost algorithm via CONF. We use the product of the label and the confidence for the observation that YCONF, x, less than or equal to 0 if and only if the classifier is incorrect. The theorem we'll prove in this post is theorem, with high probability over a random choice of training data, for any 0. Pair train margin, x, less than or equal to theta. In words, the generalization error of the boosting hypothesis is bounded by the distribution of margins observed on the training data. To state and prove the theorem more generally, we have to return to the details of Pockler. Here and in the rest of this post, PRD denotes PRXD, the probability over a random example drawn from the distribution D, and PRS denotes the probability over a random training set of examples drawn from D. Theorem: let S be a set of M random examples chosen from the distribution D generating the data. Assume the weak learner corresponds to a finite hypothesis space H of size H, and let delta 0. Then with probability at least 1, delta, over the choice of S, every weighted majority vote function F satisfies the following generalization bound for every theta 0. PRDYF, x, less than or equal to 0 less than or equal to PRSYF, x, less than or equal to theta plus O, 1 log H theta 2 plus log, 1 slash delta. From now on, a majority vote function F, x, will mean to take the sign of. In other words, this phenomenon is a fact about voting schemes, not boosting in particular. From now on, a majority vote function F, x, will mean to take the sign of a sum of the form sigma I equals 1 ai, x, where ai greater than or equal to 0 and sigma I equals 1. This is the convex hull of the set of weak learners H. If H is infinite, in our proof it will be finite, but we'll state a generalization afterward, then only finitely many of the ai in the sum may be non-zero. To prove the theorem, we'll start by defining a class of functions corresponding to unweighted majority votes with duplicates. Definition: let Cn be the set of functions f, x, of the form 1 and sigma I equals 1 and hi, x, where high set membership symbol h and the high may contain duplicates. Some of the high may be equal to some other of the hj. Now every majority vote function f can be written as a weighted sum of high with weights ai. I'm using a instead of alpha to distinguish arbitrary weights from those weights arising from boosting. So any such f, x, defines a natural distribution over h where you draw function high with probability ai. I'll call this distribution af. If we draw from this distribution n times and take an unweighted sum, we'll get a function g, x, set, call the random process, distribution, generating functions in this way qf. In diagram form, the logic goes: f rightward arrow weights ai rightward arrow distribution over h rightward arrow function in Cn by drawing n times according to a. The main fact about the relationship between f and qf is that each is completely determined by the other. Obviously qf is determined by f because we defined it that way, but f is also completely determined by qf as follows: f, x, equals egq. Proving the equality is an exercise for the reader. Proof of theorem. First we'll split the probability PRDYF, x, less than or equal to 0 into two pieces, and then bound each p. First a probability reminder. If we have two events a and b, in what's below, this will be yg, x, less than or equal to theta slash 2 and yf, x, less than or equal to 0, we can split up PRA into PRA and b plus PRA and b, where b is the opposite of b. This is called the law of total probability. Moreover, because PRA and b equals PRAB PRB and because these quantities are all at most 1, it's true that PRA and b less than or equal to PRAB, the conditional probability, and that PRA and b less than or equal to PRB. Back to the proof. Notice that for any g, x, set membership symbol Cn and any theta 0, we can write PRDYF, x, less than or equal to 0 as a sum. PRDYF, x, less than or equal to 0 equals PRDYG, x, less than or equal to theta slash 2 and yf, x, less than or equal to. Now I'll loosen the first term by removing the second event, that only makes the whole probability bigger, and loosen the second term by relaxing it to a conditional. PRDYF, x. Now because the inequality is true for every g, x, set membership symbol Cn, it's also true if we take an expectation of the RHS over any distribution we choose. We'll choose the distribution qf to get PRDYF, x, and T1, term 1, is T1 and T2 is PR. We can rewrite the probabilities using expectations because 1. The variables being drawn in the distributions are independent, and 2. The probability of an event is the expectation of the indicator function of the event. Now we'll bound the terms T1 T2 separately. We'll start with T2. Fix xy and look at the quantity inside the expectation of T2. PRGQFYG, x. This should intuitively be very small for the following reason. We're sampling g according to a distribution whose expectation is f, and we know that yf, x, less than or equal to 0. Of course yg, x, is unlikely to be large. Mathematically we can prove this by transforming the thing inside the probability to a form suitable for the Kernoff bound. Saying yg, x, theta slash 2 is the same as saying yg, x, eyg, x, theta slash 2, i.e. that some random variable which is a sum of independent random variables, the high, deviates from its expectation by at least theta slash 2. Since the y's are all plus or minus 1 and constant inside the expectation, they can be removed from the absolute value to get less than or equal to PRGQF. The Kernoff bound allows us to bound this by an exponential in the number of random variables in the sum, i.e. n. It turns out the bound is en theta 2 slash 8. Now recall T1. T1 equals PRXDGQ. For T1, we don't want to bound it absolutely like we did for T2, because there is nothing stopping the classifier f from being a bad classifier and having lots of error. Rather, we want to bound it in terms of the probability that yf, x, less than or equal to theta. We'll do this in two steps. In step 1, we'll go from PRD of the g's to PRS of the g. Step 1, for any fixed g theta, if we take a sample s of size m, then consider the event in which the sample probability deviates from the true distribution by some value epsilon n, the event. PRDYG. The claim is this happens with probability at most e2m epsilon n2. This is again the Kernoff bound in disguise, because the expected value of PRS is PRD, and the probability over s is an average of random variables. It's a slightly different form of the Kernoff bound. See this post for more. From now on we'll drop the excess when writing PRS. The bound above holds true for any fixed g theta, but we want to bound over all g in theta. To do that we use the union bound. Note that there are only n plus 1 possible choices for a non-negative theta because g, x, is a sum of n values each of which is either plus or minus 1. And there are only cn less than or equal to h n possibilities for g, x. So the union bound says the above event will occur with probability at most n plus 1, hn e2m epsilon n2. If we want the event to occur with probability at most delta n, we can judiciously pick epsilon n equals 1 slash 2m. And since the bound holds in general, we can take expectation with respect to qf and nothing changes. This means that for any delta n, our chosen epsilon n ensures that the following is true with probability at least 1 delta n PRD. Now for step 2, we bound the probability that yg, x, less than or equal to theta slash 2 on a sample to the probability that yf, x. Step 2, the first claim is that PRSGQFYG, x. What we did was break up the LHS into 2 and s, when yf, x, theta and yf, x, less than or equal to theta, this was still an equality. Then we loosen, now we have the then we loosen the first term to PRSYF, x, less than or equal to theta. Then we loosen the second term again using the fact that a probability of an n is. Now we have the probability of yg, x, less than or equal to theta slash 2 bounded by the probability that yf, x, less than or equal to 0 plus some stuff. We just need to bound the plus some stuff absolutely and then we'll be done. The argument is the same as our previous use of the Kernoff bound. We assume yf, x, greater than or equal to theta, and yet yg, so the deviation of yg, x, from its expectation is large, and the probability, and again we use the union bound to ensure the failure of this bound for any n will be very small. Specifically, if we want the total failure probability to be at most delta, then we need to pick some delta js so that delta e, putting everything together, we get that with probability at least 1 delta for every theta and every n, this bound on the failure probability of f, x. PRXDYF, x, less than or equal to 0 less than or equal to p. This claim is true for every n, so we can pick n that minimizes it. Doing a little bit of behind the scenes calculus that is left as an exercise to the reader. A tight choice of n is 4 slash theta, 2 log, m slash log h. We proved this for finite hypothesis classes, and if you know what VC dimension is, you'll know that it's a central tool for reasoning about the complexity of infinite hypothesis classes. An analogous theorem can be proved in terms of the VC dimension. In that case, calling D the VC dimension of the weak learners, how can we interpret these bounds with so many parameters floating around? That's where asymptotic notation comes in handy. If we fix theta less than or equal to 1/2 and delta equals 0.01, then the big O part of the theorem simplifies to log h log m slash m, which is easier to think about since log m slash m goes to 0 very fast. Now the theorem we just proved was about any weighted majority function. The question still remains, why is AdaBoost good? That follows from another theorem, which we'll state and leave as an exercise. It essentially follows by unwrapping the definition of the AdaBoost algorithm from last time. Theorem, suppose that during AdaBoost the weak learners produce hypotheses with training errors epsilon 1, epsilon t. Then for any theta, pr, xy, syf, x, let's interpret this for some concrete numbers. Say that theta equals 0 and epsilon t is any fixed value less than 1/2. In this case the term inside product becomes epsilon, 1 epsilon. On the other hand, if we raise theta to about 1/3, then in order to maintain the LHS tending to 0 we would need epsilon. If you're interested in learning more about boosting, there is an excellent book by Freund and Shapiro, the inventors of boosting, called Boosting, Foundations and Algorithm. There they include a tighter analysis based on the idea of Rademacher complexity. The bound I presented in this post is nice because the proof doesn't require any machinery past basic probability, but if you want to reach the cutting edge of knowledge about boosting you need to invest in the technical stuff. Until next time, share this. Click to share on Facebook, opens a new window. Click to share on Reddit, opens a new window. Click to share on Twitter, opens a new window.
Machine learning. Sounds so complicated, but it's not so complicated. StatQuest. Hello, I'm Josh Starman. Welcome to StatQuest. Today we're going to cover AdaBoost, and it's going to be clearly explained. Note, this StatQuest shows how to combine AdaBoost with decision trees, because that is the most common way to use AdaBoost. So, if you're not familiar with
I think I remember seeing this video before.
decision trees, check out the quest. We will also mention random forests, so if you don't know about them, check out the quest. We'll start by using decision trees and random forests to explain the three concepts behind AdaBoost. Then we'll get into the nitty-gritty details of how AdaBoost creates a forest of trees from scratch and how it's used to make classifications. So let's start by using decision trees and random forests to explain the three main concepts behind AdaBoost. In a random forest, each time you make a tree, you make a full-sized tree. Some trees might be bigger than others, but there's no predetermined maximum depth. In contrast, in a forest of trees made with AdaBoost, the trees are usually just a node and 2 leaves. Oh no, it's the dreaded terminology alert. A tree with just 1 node and 2 leaves is called a stump. So this is really a forest of stumps rather than trees. Stumps are not great at making accurate classifications. For example, if we were using this data to determine if someone had heart disease or not, then a full-size decision tree would take advantage of all 4 variables that we measured: chest pain, blood circulation, blocked arteries, and weight, to make a decision. But a stump can only use 1 variable to make a decision. Thus, stumps are technically weak learners. However, that's the way AdaBoost likes it, and it's one of the reasons why they're so commonly combined. Now back to the random forest. In a random forest, each tree has an equal vote on the final classification. This tree's vote is worth just as much as this tree's vote, or this tree's vote. In contrast, in a forest of stumps made with AdaBoost, some stumps get more say in the final classification than others. In this illustration, the larger stumps get more say in the final classification than the smaller stumps. Lastly, in a random forest, each decision tree is made independently of the others. In other words, it doesn't matter if this tree was made first, or this one. In contrast, in a forest of stumps made with AdaBoost, order is important. The errors that the first stump makes influence how the second stump is made, and the errors that the second stump makes influence how the third stump is made, etc., etc., etc. To review, the 3 ideas behind AdaBoost are: 1. AdaBoost combines a lot of weak learners to make classifications. The weak learners are almost always stumps. 2. Some stumps get more say in the classification than others.
Maybe a good idea that I'm just thinking about now is to create an article about the counterfactual regret minimization technique of one of the AI's uses, or the policy, I forgot how it's called. I think policy agent or something like that, where each agent creates a state of the game or something like that. Remember, there's this guy called Norman Brown, I think, and he did the algorithms for poker. So maybe I should do an article about those things, and that will allow me to study the algorithms for finding the Nash equilibrium in poker. While I think that's a good idea, actually. I might do that. So I'm gonna finish this article here. I'm probably not gonna change much on these articles, so I'm just gonna review, see if it's correct. But I don't think I'm gonna put anything. Maybe I'll remove some parts as well, and then check the code to see if it's correct. It's not that hard because it's using libraries, so the hard part is on creating the libraries themselves with that I remember like studying at some point as well. Like doing the code for the matrices, multiplication, that kind of stuff is hard, but understanding how these libraries work is not hard at all, I think. It's a lot easier than the other stuff. The extended Euclidean algorithm, for example. So I think I'm gonna do this one, and then I might, because there's only 6 minutes left here, I'm gonna stop. Then I might create another category inside of the algorithms called poker, and then just I think I'm gonna search for this stuff. So that way I kill 2 birds with 1 stone. I make the articles about poker, and I study maybe I can even try to implement one. All these algorithms, this artificial intelligence for poker, and then use my hands to play against it, let's say, or use use the data that I have to calculate the Nash against the data. I think that would be extremely interesting. No, I know he has a YouTube channel, and I've listened or watched through this stuff. And this is the stuff that I'm talking about. So I think I'm gonna do that. Maybe I can place this in the 3 articles as well. I have to see. I'm gonna see which. I'm gonna watch these videos again, I think, and see which kind of a AI algorithm is using, which kind of a technique, and then I'm gonna place that technique on ChatGPT to create an article, and then I'm gonna review those articles and while I build the poker tool. I'm gonna think about this off stream, but I think I might do that. Because I also want to review the other articles as well. There's a bunch of articles to do, so I don't know which one is best to do first. But I think this sounds like a very interesting idea.
3. Each stump is made by taking the previous stump's mistakes into account. Bam! Now let's dive into the nitty-gritty detail of how to create a force of stumps using AdaBoost. First, we'll start with some data. We create a force of stumps with AdaBoost to predict if a patient has heart disease. We will make these predictions based on a patient's chest pain and blocked artery status and their weight. The first thing we do is give each sample a weight that indicates how important it is to be correctly classified. Note, the sample weight is different from the patient weight, and I'll do the best I can to be clear about which of the two I'm talking about. At the start, all samples get the same weight. 1 divided by the total number of samples. In this case, that's 1 divided by 8. And that makes the samples all equally important. However, after we make the first stump, these weights will change in order to guide how the next stump is created. In other words, we'll talk more about the sample weights later. Now we need to make the first stump in the forest. This is done by finding the variable, chest pain, blocked arteries, or patient weight that does the best job classifying the samples. Note, because all of the weights are the same, we can ignore them right now. We start by seeing how well chest pain classifies the samples. Of the 5 samples with chest pain, 3 were correctly classified as having heart disease, and 2 were incorrectly classified. Of the 3 samples without chest pain, 2 were correctly classified as not having heart disease, and 1 was incorrectly classified. Now we do the same thing for blocked arteries, and for patient weight. Note, we used the techniques described in the decision tree StatQuest to determine that 176 was the best weight to separate the patients. Now we calculate the Gini index for the 3 stumps. The Gini index for patient weight is the lowest, so this will be the first stump in the forest. Now we need to determine how much say this stump will have in the final classification. Remember, some stumps get more say in the final classification than others. We determine how much say a stump has in the final classification based on how well it classified the samples. This stump made one error. This patient, who weighs less than 176, has heart disease, but the stump says they do not. The total error for a stump is the sum of the weights associated with the incorrectly classified samples. Thus, in this case, the total error is 1/8. Note, because all the sample weights add up to 1, total error will always be between 0 for a perfect stump and 1 for a horrible stump. We use the total error to determine the amount of say this stump has in the final classification with the following formula. Amount of say equals 1/2 times the log of 1 minus the total error divided by the total error. We can draw a graph of the amount of say by plugging in a bunch of numbers between 0 and 1 for total error. The blue line tells us the amount of say for total error values between 0 and 1. When a stump does a good job and the total error is small, then the amount of say is a relatively large positive value. When a stump is no better at classification than flipping a coin, i.e. half the stumps are correctly classified and half are incorrectly classified, and the total error equals 0.5, then the amount of say will be 0. And when a stump does a terrible job and the total error is close to 1, in other words, if the stump consistently gives you the opposite classification, then the amount of say will be a large negative value.
I forgot to run the blockchain stuff. I don't know why I'm putting like this.
So if a stump votes for heart disease, the negative amount of say will turn that vote into not heart disease. Note, if total error is 1 or 0, then this equation will freak out. In practice, a small error term is added to prevent this from happening. With patient weight greater than 176, the total error is 1/8, so we just plug and chug. And the amount of say that this stump has in the final classification is 0.97. Bam! Now that we've worked out how much say this stump gets when classifying a sample, let's work out how much say the chest pain stump would have if it had been the best stump. Note, we don't need to do this, but I think it helps illustrate the concepts we covered so far. Chest pain made 3 errors, and the total error equals the sum of the weights for the incorrectly classified samples. So the total error for chest pain is 3/8. We can get a sense of what the amount of say will be by looking at the graph when total error equals 3/8. So we are expecting the amount of say to be between 0 and 0.5. Now we plug 3/8 into the formula for the amount of say and do the math. And the amount of say that the chest pain stump would have had on the final classification is 0.42. I'll leave the blocked artery stump as an exercise for the viewer. Now we know how the sample weights for the incorrectly classified samples are used to determine the amount of say.
It's gonna start running the node.
Each stump gets. Bam! Now we need to learn how to modify the weights so that the next stump will take the errors that the current stump made into account. Let's go back to the first stump that we made. When we created this stump, all of the sample weights were the same. And that meant we did not emphasize the importance of correctly classifying any particular sample. But since this stump incorrectly classified this sample, we will emphasize the need for the next stump to correctly classify it by increasing its sample weight and decreasing all of the other sample weights. Let's start by increasing the sample weight for the incorrectly classified sample. This is the formula we will use to increase the sample weight for the sample that was incorrectly classified. We plug in the sample weight from the last stump, and we scale 1/8 with this term. To get a better understanding of how this part will scale the previous sample weight, let's draw a graph. The blue line is equal to e raised to the amount of say. When the amount of say is relatively large, i.e. the last stump did a good job classifying samples, then we will scale the previous sample weight with a large number. This means that the new sample weight will be much larger than the old one. And when the amount of say is relatively low, i.e. the last stump did not do a very good job classifying samples, then the previous sample weight is scaled by a relatively small number. This means that the new sample weight will only be a little larger than the old one. In this example, the amount of say was 0.97, and e raised to 0.97 equals 2.64. That means the new sample weight is 0.33, which is more than the old one. Bam. Now we need to decrease the sample weights for all of the correctly classified samples. This is the formula we will use to decrease the sample weights. The big difference is the negative sign in front of amount of say. Just like before, we plug in the sample weight. And just like before, we can get a better understanding of how this will scale the sample weight applying a graph using different values for amount of say. The blue line represents e raised to the negative amount of say. When the amount of say is relatively large, then we scale the sample weight by a value close to 0. This will make the new sample weight very small. If the amount of say for the last stump is relatively small, then we will scale the sample weight by a value close to 1. This means that the new sample weight will be just a little smaller than the old one. In this example, the amount of say was 0.97, and e raised to negative 0.97 equals 0.38. The new sample weight is 0.05, which is less than the old one. Bam. We will keep track of the new sample weights in this column. We plug in 0.33 for the sample that was incorrectly classified. All the other samples get 0.05. Now we need to normalize the new sample weights so that they will add up to 1. Right now, if you add the new sample weights, you get 0.68. So we divide each new sample weight by 0.68 to get the normalized values. Now, when we add the new sample weights, we get 1, plus or minus a little rounding error. Now we just transfer the normalized sample weights to the sample weights column, since those are what we will use for the next stump. Now we can use the modified sample weights to make the second stump in the forest. Bam. In theory, we could use the sample weights to calculate weighted gene indexes to determine which variable should split the next stump. The weighted gene index would put more emphasis on correctly classifying the sample, the one that was misclassified by the last stump, since this sample has the largest sample weight. Alternatively, instead of using a weighted gene index, we can make a new collection of samples that contains duplicate copies of the samples with the largest sample weights. So we start by making a new but empty dataset that is the same size as the original. Then we pick a random number between 0 and 1, and we see where that number falls when we use the sample weights like a distribution. If the number is between 0 and 0.7, then we would put this sample into the new collection of samples. And if the number is between 0.7 and 0.14, then we would put this sample into the new collection of samples. And if the number is between 0.14 and 0.21, then we would put this sample into the new collection of samples. And if the number is between 0.21 and 0.70, then we would put this sample into the new collection of samples, etc., etc. For example, imagine the first number I picked was 0.72. Then I would put this sample into my new collection of samples. Then I pick another random number and get 0.42. And I would put this sample into my new collection of samples. Then I pick 0.83. And I would put this sample into my new collection of samples. Then I pick 0.51. And I would put this sample into my new collection of samples. Note, this is the second time we add this particular sample to the new collection of samples. We then continue to pick random numbers and add samples to the new collection until the new collection is the same size as the original. Ultimately, this sample is added to the new collection of samples 4 times, reflecting its larger sample weight. Now we get rid of the original samples and use the new collection of samples. Lastly, we get all the samples equal sample weights, just like before. However, that doesn't mean the next stump will not emphasize the need to correctly classify these samples. Because these samples are all the same, they will be treated as a block, creating a large penalty for being misclassified. Now we go back to the beginning and try to find a stump that does the best job classifying the new collection of samples. So that is how the errors that the first tree makes influence how the second tree is made, and how the errors that the second tree makes influence how the third tree is made, etc., etc., etc. Double bam. Now we need to talk about how a force of stumps created by AdaBoost makes classifications. Imagine that these stumps classify the patient as has heart disease, and these stumps classify the patient as does not have heart disease. These are the amounts of say for these stumps, and these are the amounts of say for these stumps. Now we add the amounts of say for this group of stumps, and for this group of stumps. Ultimately, the patient is classified as has heart disease because this is the larger sum. Triple down. To review, the 3 ideas behind AdaBoost are: 1. AdaBoost combines a lot of weak learners to make classifications. The weak learners are almost always stumps. 2. Some stumps get more standard classification than others. And 3. Each stump is made by taking the previous stump's mistakes into account. If we have a weighted gene function, then we use it with the sample weights. Otherwise, we use the sample weights to make a new dataset that reflects those weights. Hooray! We've made it to the end of another exciting StatQuest. If you like this StatQuest and want to see more, please subscribe. And if you want to support StatQuest, well, consider buying a t-shirt.
When I finish reading this article here, then I'm gonna stop.
AdaBoost for Dummies, breaking down the math and its equations into simple terms. Learning machines is a long walk up the stairs, but we can shorten the path. Photo by Gabriel is Dion Unsplash. AdaBoost, shortened for adaptive boosting, is a machine learning approach that is conceptually easy to understand, but less easy to grasp mathematically. Part of the reason those two equations and formulas not being broken down into simple terms with basic math is demonstration of the equations. This essay intends to do just that with AdaBoost, with newcomers into data science as the primary target audience. There are many wonderful lectures, videos, and papers that effectively and neatly explain the concept behind AdaBoost. Simply put, the idea is to set weights to both classifiers and data points, samples, in a way that forces classifiers to concentrate on observations that are difficult to correctly classify. This process is done sequentially in that the two weights are adjusted at each step as iterations of the algorithm proceed. This is why AdaBoost is referred to as a sequential ensemble method, ensemble referring to a type of learning that combines several models to improve the final predictive performance. The concept is easy to follow, but once we try to dig a little deeper to understand the math that supports the concept, we become faced with many articles and lectures with this similar looking site. For those without academic background in math and / or the non-math types now studying data science following the recent machine learning boom, the notations alone can seem quite daunting. This article intends to clear away the confusion and the intimidation by breaking down the notations and the formula, and using simple math to explain how AdaBoost work. Basic terminologies. First, let's go over some basic terminologies. Boosting, combining many weak, simple learners to create a highly accurate weak learners, classifiers that produce prediction that is slightly better than random guessing. Random guessing is equivalent to 50%, like flipping a coin. This will be familiar to those who are conversant with information theory, particularly the idea of Shannon's entropy. Hypothesis, our classifier, aka the function that our machine learning algorithm makes to approximate the unknown function, the target, true, function, which models the relationship between the input values x and output values y. AdaBoost, the first practical boosting algorithm invented by Freund and Shapiro, 1995. It is based on Vapnik and Chervonkey's idea that for a trained classifier to be effective and accurate in its predictions, it should meet these 3 conditions. 1. Classifier should be trained on enough training examples. 2. It should provide a good fit to these examples by producing low training error. 3. It should be simple, in that simpler models are better than overly complex one. Explaining AdaBoost, one step at a time. Let us go over the iterative formula, breaking down every notation at each step on a granular level for easy digestion. 1. Given, x_1 y_1, comma, x_, set membership symbol, element of set x, if a equals 1, 2, 3, 7, 2 set membership symbol a, x_1, y_1 first training sample, x_m, y_m, equals. Now that we have all the notations down, we can read that the first part of the formula is, given the training set containing m samples where all x inputs are an element of the total set x and where y outputs are an element of a set comprising of only 2 values, -1, negative class, and 1, positive class. 2. Initialize, d1, I, equals 1/m for I equals 1, m. Here, d equals weights of samples and I equals the ith training sample. In other papers, the d will be written as w. Thus the next statement reads, initialize all weights of your samples to 1 divided by number of training sample. 3. For t equals 1, t, asterisk train weak learner using distribution dt asterisk game, select h_t with low weighted error. Epsilon equals pr_i dth_t, 11, not equal to y_i. Asterisk choose alpha_t equals 1/2 asterisk ln, 1 epsilon/epsilon. dt plus 1, I, equals dt, I, exp, dash alpha t asterisk y_i asterisk h_t, x_i, slash z. Useful notations. PR equals probability. h_t equals hypothesis/classifier. Epsilon equals minimum misclassification error for the model. Alpha equals weight for the classifier. exp equals Euler's E. 2. zt equals normalization factor, used to ensure that weights represent a true distribution. With these notations at hand, we can read the next portion as, for t equals 1 to t classifiers, fit it to the training data, where each prediction is either -1 or 1, and select the classifier with the lowest weighted classification error. The formula to formally compute epsilon is described as follows. Let's break down this particular model. Useful notations. Y underscore I not equal to H.
So it pretty much creates a sequence of trees, and each tree is based on that decision, weak decision, and that weak decision creates a weight based on whether or not which one was correct or not, and that creates a weight for them, and that's going to determine what is going to be the next decision tree. And then it does that over and over again until it has all the weights calculated to the highest accuracy that it can get. So it's not that hard to understand, I think. The math is hard, but the concept is easy.
W underscore I equals weight. Thus, the formula reads, error equals the sum of the misclassification rate, where weight for training sample I and Y underscore I not being equal to our prediction H underscore J, which equals 1 if misclassified and 0 if correctly classified, dot. Let us apply simple math to make sense of the formula. Consider having 4 different samples with weights 0.5, 0.2, 0.1, and 0.04. Imagine our classifier H predicted values 1, 1, minus 1, and minus 1, predicted, 1, 1, actual, weights, 1 or 0. This leads to the following calculation for the misclassification rate. Misclassification rate slash error equals 0.51 plus 0.20 plus 0.1, error equals 0. Next, choose our weight for the classifier, alpha, by the formula that reads 1/2 asterisk ln, 1 error slash error. Simple math might explain better than words could. Assume, for instance, that we have errors 0.30, 0.70. Our classifier weights would be calculated as alpha equals 1/2 epsilon equal alpha equals 1 alpha equals 1/2 asterisk. Notice 3 interesting observations. 1. Classifier with accuracy higher than 50% results in a positive weight for the classifier. In other words, alpha 0 if epsilon. Now comes the very important part of the equation, updating the weights for each sample. I have mentioned above that the point of the update is to force classifiers to concentrate on observations that are difficult to correctly classify. This is done by making misclassified cases to be updated with increased weights after an iteration. Increased weights would make our learning algorithm pay higher attention to these observations in the next iteration. Conversely, correctly classified cases would receive a decreased weight and reduced attention by our classifiers in the next iteration. Again, with simple numbers as demonstration, information uptake is painless. Let us use the error rate of 0.3 above to plug into the formula. Remember that we are looking for the low weighted error. In other words, we should not use error rate from n above 0.5. With the low error rate, let us check what happens when cases are misclassified and when cases are correctly classified. Misclassified. Correctly classified, and there you have it. In the case of incorrect classification, the exp term became larger than 1, and in the case of correct classification, the exp term became below. Therefore, incorrect classification would receive higher weights, prompting our classifiers to pay more attention to them in the next iteration, while the opposite case of correct classification would result in the convert. We continue this iteration until a low training error is achieved, or b preset number of weak learners have been added. This is a parameter that is under our control. We then take the final prediction by adding up the weighted prediction of every classifier. We have seen how AdaBoost works in a granular level, by breaking down every notation in the formula. We have then applied simple math to understand how each component of the formula works. This practice of approaching formulas through its decomposed parts can be a useful practice for understanding machine learning algorithm, more from towards data science. Your home.
Yeah, let me read this before I stop. Well, boosting is a machine learning sample technique that combines multiple weak models to create a single strong model. The basic idea behind boosting is to train a sequence of weak models, where each model focuses on correcting the mistakes made by the previous model. The final model is then formed by combining the weak models using a weighted average. The key advantage of boosting is that it can improve the performance of weak models by focusing on the examples that are difficult to classify correctly. How does AdaBoost work? AdaBoost is an iterative algorithm that trains a sequence of weak models. In each iteration, the algorithm gives a higher weights to the examples that were misclassified by the previous model. It trains the next model to focus on these examples. The final model is then formed by combining the weak models using weighted averages. The basic step of the AdaBoost algorithms are as follows. Initialize the weights of the examples, train a weak model on the training data, update the weights of the examples based on the performance of the current model. Repeat steps 2 and 3 until a stopping criterion is met, such as a maximum number of iterations or a desired accuracy level. Combine the weak models using weighted averages to form the final model. AdaBoost is a simple and effective algorithm that can produce strong results with relatively little data. However, it can also be sensitive to noise data and outliers. It is important to pre-process the data and choose appropriate weak models for the task at hand. What are weak models in AdaBoost? A weak model in AdaBoost is simply a model that is slightly better than random guessing. Any machine learning algorithm can be used as a weak model in AdaBoost as long as it can make predictions that are slightly better than random. Common weak models used in AdaBoost include decision trees, logistic regression, and support vector machines. Choosing the right weak model. The choice of weak model can have a significant impact on the performance of the AdaBoost algorithm. In general, it is recommended to use simple models as weak models, since they are less prone to overfitting and can be trained more quickly. However, the choice of weak model will also depend on the specific problem at hand and the type of data being used. For example, if the data is noisy and contains many outliers, it may be better to use a robust model, such as a support vector machine, as the weak model. On the other hand, if the data is well behaved and has a clear decision boundary, a simple decision tree may be a better choice. Advantages and disadvantages of AdaBoost. AdaBoost has several advantages, including its simplicity, versatility, and ability to produce strong results with relatively little data. However, it also has some disadvantages, such as its sensitivity to noise, data, and outliers, and its tendency to be slower than other boosting algorithms. One of the key advantages of AdaBoost is its simplicity. The algorithm is easy to understand and implement, making it a good choice for beginners. AdaBoost is versatile, so it can be used with a wide range of weak models, including decision trees. Yeah, I think this part I'm gonna remove because it's kind of redundant. And I think as far as I read, it's pretty much the same. Like, it's very congruent with the other stuff. So I think all of this stuff is correct. That's pretty much what it is. It's not hard to understand, I think, how it works. Obviously, if I wanted to understand more the math and the source code, then I think I would spend a lot more time reading the papers to understand how exactly the math works there, to select the weights at each iteration, because obviously that's going to impact how the accuracy is in the end, because it changes the flow from one tree to the other, obviously, through the mathematics you choose. But I'm not going to focus too much on this one. How does AdaBoost work? I already read that. Yeah, I think now let's just look at this algorithm. Estimators, learning rate, and the alphas, which are the stuff that is used to calculate the weights at each iteration, as far as I understand now. X shape. So this uses a decision tree classifier as the weak model. Then it fits the data with the decision tree and predicts different than y, which is the testing. I always forget how to say each one. But pretty much you have the data you train, then I think, yeah, the data you test and the data you train. But here is using the same one, so not really sure about this. Oh no, is using the different. No, it's the same X as well. So not really sure if this is correct. I'm gonna put this code on ChatGPT and just ask. And this is the calculations of the weight using the Euler, however you say that, and the alpha plus or times the incorrect predictions, which is gonna change the weight for the next iteration of the tree. Well, it's because it's two different functions, obviously. So yeah, but it's still weird that it uses the same data to fit the data with the decision tree, and then to create the predictions. I'll put the code on ChatGPT. It does not use a separate task set during training, but rather it trains each decision tree on the entire training dataset and then evaluates the performance to update the weights of the sample for the next iteration. The algorithm focus on learning from the mistakes of the previous models. So I guess it doesn't matter that the weak model is gonna have an overfitted prediction in the first, because on each iteration is gonna update the weights, and that's what matters. So I think that's what's going on. And then the thing here is just the math. There is the sum of the weight times incorrect, which are the values of the incorrect predictions. It, the weight is a vector of the sample, vector of one of the sample divided by the sample. So it's 1 divided by the sample. The beginning weight, because all of them are going to be equal. Is the whole thing that I was explaining in the video about the 1 divided by 8. That all of them start with the same weight. So I want to understand how you can multiply the weight based on the Boolean values on this formula here to get the error. Maybe the Boolean can be expressed as zeros or ones. But if you're using this operator, I think it would return false or true. Not sure if I wrote correctly, but doesn't matter. Python Boolean values true and false can be, yeah, that's what I was thinking. So it's a mask is basically using zeros and ones. So it's gonna fit and it's gonna fit with the same weight in the beginning, and then it's gonna predict with the same data because it doesn't matter in the beginning. And then this is gonna be an array of zeros and ones, and this is gonna be multiplied by the initial weights and divided by the sum of the weights. That's gonna be the error. That is used to calculate this alpha, which is gonna be what determines what which tree is created in the next iteration of the loop. Because it's going to change the weights here of the prediction based on these equations. So I think this is correct. I'm going to put this article there on the website. AdaBoost is a simple and effective boosting algorithm that has been widely used for a variety of machine learning problems. Despite its simplicity, AdaBoost can produce strong results with relatively little data, making it a useful algorithm for problems where the data is limited. However, it is important to be aware, such as its sensitivity, blah, blah, blah. Let's see here. I also have to open this thing here. Change the status of the thing. Yeah, I think I'm gonna stop here. I might come back today, and I think if I come back today, well, I'm gonna decide off stream whether or not I'm gonna watch these videos off stream. And then if I come back, there might be a chance that I start working on this poker algorithm again, or poker software. I think I'm gonna redo the stuff that I did on Rust. I'm gonna translate that into Python because it's gonna be a lot easier to do things in Python, I think. And then I might use ChatGPT to write articles about this poker stuff here, and then also review the articles, maybe build the software first, the beginning of the parsing, because that's gonna be really annoying. I remember that there were several challenges there where, because I have to keep track of the cycle of the iteration there based on the control flow, and I used matching in Rust and regex. So that might be very annoying. It might take a lot more time than I'm expecting. So I want to get that out of the way first, I think, if I'm gonna build this stuff on Python. And then once I get to the point where I am going to connect with PySolver, then maybe I'll just study this stuff and try to implement a machine learning algorithm for poker, and that I don't use the Pio then. It might be easier that way because then I can format the data however I want. But I think either way is going to be difficult when it comes to connecting with Pio because you have to think about how you're going to create the ranges using the data. So I might not do that because it might take too much time and then it's going to deviate too much of the focus that I have on writing the articles and going back to the blockchain. I'm going to think about it. The good side of this is then I kill two birds with one stone, where I become better at poker and also write the articles and study machine learning at the same time. But the downside is then it's going to deviate the focus from the stuff that I'm doing, which is something that I tend to do as well. So I'm going to think more about this. But I might probably going to come back today to either continue to review the articles or to build this poker tool. And if I don't, then very likely come back tomorrow, or yeah, very